Welcome everyone to the Asia Pacific Analysis and PDE seminar. It's a great pleasure to introduce today's speaker, who has very kindly woken up early in the morning in Italy to give us this talk. So the speaker is Ilaria Fragala from the Politecnico di Milano, and she is going to talk to us about concavity properties of solutions to Rubin problems. Thanks, Ilaria.
Thank you very much. Thanks a lot to all the organizers for inviting me to speak in this seminar. It is a great pleasure. And the results I'm going to discuss today have been obtained in joint work with Graziano Crasta, who is in the University of Roma, La Sapienza, and concern concavity properties of solution to Rubin problems. So I would like to start with some comments on the keywords appearing in this title that just say concavity and Rubin. So let me say that among geometric properties of solutions to PDEs, the study of concavity ones plays somehow a central role, and in fact there is a very vast literature on it. As general references, I can address to the monograph by Cavol for results up to the 80s, and then to a survey paper by Guan and Mai, Contemporary Mathematics in 2005 for more recent results. And essentially, all known results concern problem under Dirichlet boundary conditions, under homogeneous Dirichlet boundary conditions. On the other hand, the study of Rubin boundary value problems is an emerging field where very little is known, and actually there is plenty of open questions. Let me recall that Rubin boundary value problems, the Rubin boundary condition, is written in the following way. It is also called oblique boundary condition, and mu here is the unit outer normal to the boundary of omega, while beta is a real parameter, which in general may have a sign, but I will always confine myself to the case when beta is positive. So when beta ranges from 0 to plus infinity, this kind of boundary conditions, which from a physical point of view, if you have in mind the diffusion equation corresponds to a partially insulated medium, range from the case of homogeneous Neumann condition that you can find by putting beta equal to 0, to the case of homogeneous Dirichlet boundary conditions that you get by letting beta tend to plus infinity. And so the reason why somehow it is so difficult to treat with this kind of boundary conditions is that the presence here of the unit normal vector to the boundary links the behavior of U in a very deep way to the geometry of the domain. And as general references about Rubin boundary value problems, let me address to this paper. It is a chapter written by Bukur, Freitas, and Kennedy in an open source book about shape optimization and spectral inequalities. And also there is a more recent paper by Lodgsen in Communication in Mathematical Physics, where there is plenty of open questions and conjectures about Rubin problems. And so it is a very natural and also intriguing question to ask what about somehow the meeting, the crossway of these two subjects. And this talk is precisely about this. And
Ilaria, are you going through the pages? So far, we only see the title page. So.
Maybe it is
try
better
sharing again. Yeah, that's better. Now we didn't see that page.
Okay, so I will stay in not full screen mode, right? Okay, this is the outline of the remaining of the talk. So I will try to introduce the problem by giving some background and also some motivation to study it. And then I will briefly describe the groundbreaking negative result holding for small beta by Anders, Clutterbuck, and Hauer. And I will discuss our result, which is a positive result holding for large values of the parameter, trying also to give some hints on the proof, and finally discuss some of the many open questions. So let me say that the study of concavity properties of solutions to elliptic PDEs started in the 70s with a pioneering paper by Makar Limanov, who proved the following: if omega is a convex domain in the plane, and U is the Dirichlet torsion function of it, namely the unit solution to this boundary value problem, then the level sets of U are convex. And more specifically, U is power concave. It is 1/2 concave. And a few years later, Braskamp and Lieb proved their similar result, which states that if you have a convex domain in the Euclidean space dimension of arbitrary dimension, and U is the Dirichlet ground state of omega, namely up to a constant multiple, the unique solution to this boundary value problem, where lambda 1d denotes the first Dirichlet Laplacian eigenvalue, then as well U has again convex level lines, and this time its concavity property is precisely of being logarithmically concave, that is to say the map logarithm of U is concave in omega. And the proof methods used to obtain these two results were very different from each other. Makar Limanov used essentially a p-function argument involving the maximum principle, while Braskamp and Lieb deduced these results from the fact that the fundamental solution of the diffusion equation is itself log concave. And so later in the 80s, new methods were developed in order to try to reach a more systematic approach, working also for more general elliptic equations. In particular, Korevar invented a very nice technique nowadays known as Korevar concavity maximum principle, and Caffarelli and Friedman introduced a deformation technique that later on I will try to explain a little bit, which is called the continuity method. And these new ideas were then used and developed, refined in several works. I've mentioned some of them here, but my apologies because for sure the references are not complete. And in particular, this kind of techniques allowed to show that the concavity results in the previous slide hold in any space dimension and as a strict concavity inequalities. And then in the 90s, starting from the 90s, with the advent of viscosity theory, most efforts were devoted to extend the previous results to the case of viscosity solution to fully nonlinear PDEs. So in particular, important contributions came by Alvarez, Lasley, and Lyons, who could show the concavity of solutions to fully nonlinear PDEs of this kind under suitable structure conditions on capital F. And then by Caffarelli, Guan, and Ma, who could extend the constant rank theorem by Korevar and Lewis to the case of viscosity solutions. And finally, in the last decades, there have been several relevant refinements of concavity results in different directions. Let me mention, for instance, that Mashi and Ye have been able to obtain a lower bound and a Gaussian curvature of the solution to the torsion problem, and in a completely different direction, Aronich, Solani, and Trombetti have studied the concavity not of the torsion function, but of the difference between the maximum of such function and the function itself. But especially I wish to mention this important progress by Anderson and Clutterbuck in 2011. They were able to improve Braskamp and Lieb results by showing that the Dirichlet ground state of a convex domain in Rn satisfies a refined concavity estimate. Actually, what they obtained is an inequality of this kind, which tells that this quantity here is a modulus of concavity for the logarithm of the Dirichlet ground state. So this right-hand side is not only 0, but it is negative, strictly negative, and this quantity is essentially the derivative of the logarithm of the Dirichlet ground state in one dimension on an interval which has length equal to the diameter d of omega. And so thanks to this very, very nice result, they were able to obtain a full proof of the so-called fundamental gap conjecture, which had been formulated several decades before, independently by Vandenberg and also by Ashbob and Guria and by Yau. And this conjecture predicted that the difference between the second and first Dirichlet eigenvalue of any convex domain omega is bounded below by 3 pi squared divided by d squared. There had been, of course, previous contributions towards the conjecture, but I've not time to discuss all of them. So for those who are interested, all the related bibliography can be found in this paper by Andrews and Clutterbuck. And so in view of this result, it is very natural to wonder what happens about the Robin spectral gap, namely for the difference between the second and the first Robin eigenvalues. And it is natural to conjecture that this Robin gap should be bounded from below for any convex set omega by a positive constant gamma beta, which as beta goes from 0 to plus infinity increases from pi squared over d squared, which is the lower bound holding in the Neumann case by a classical result due to Payne and Weinberger, to the constant found by Andrews and Clutterbuck in the Dirichlet case, which is 3 pi squared divided by d squared. And actually, this kind of conjecture was stated in this paper by Andrews, Clutterbuck, and Howard, where in order to try to attack such question, they also started the study of concavity properties of solutions under Robin boundary conditions. And in particular, they consider the following question. Is the Robin ground state of a convex domain omega log concave as it happens in the Dirichlet case? And here by Robin ground state, I mean, again, the unique positive solution up to a normalization to this boundary value problem where lambda 1 beta is the first Robin eigenvalue of the Laplacian. And they observed that an affirmative answer to this question would give the gap inequality for the Robin Laplacian with a constant gamma beta, which would not be optimal. It would be just the constant in the Neumann case. Then if affirmative, namely if the log concavity is satisfied, one could try to improve it as they did in the Dirichlet case in order to get the optimal lower bound. But it would be already a new result to get the inequality with this non-optimal constant. And let me add that one can try to make some explicit computations, of course, for a few geometries, for very simple geometries such as balls or rectangles, or if you wish, parallelepipeds in any space dimension. And these explicit computations suggest that the answer to this question should be positive, because it turns out that the Robin ground state of balls and rectangle is indeed log concave for all values of the parameter beta. And in a similar way, it is also natural to wonder whether the concavity property is preserved for the Robin torsion function. Is it true that, as it happened in the Dirichlet case, it is power concave, precisely 1/2 concave? And now for people loving surprises, here is a nice one. Here is a tweet by Julie Clutterbuck in 2018, which states that under Robin boundary conditions, the ground state needs not be log concave, unlike the Dirichlet case. And let me say that the most spectacular aspect of their result is that it involves, in a deep way, the geometry of the underlying domain. And so to recall the results, I need to introduce some terminology. So they work with convex polyhedra in Rn. So given a convex polyhedron in Rn, I need to say what is meant by saying that it is a circumsolid. So omega is called a circumsolid if there is a ball which is tangent to all its faces. So in these figures that I've taken from their paper, you can see some examples of circumsolids in the plane. All of these polygons are circumsolids because, as you can see, there is this ball which is tangent to all the faces of the polygon. While if you want an example of a polygon which is not a circumsolid, it is enough that you start, for instance, from this quadrilateral and you cut a side, you transform it into a pentagon by adding a side sufficiently far from this ball so that the ball is not touched by the new side. And here You may see further examples in 3D. Here is a tetrahedron, and here is a regular dodecahedron. Both of them are examples of circumsolids in 3D. Furthermore, what is a product of circumsolids? Well, a product of circumsolids is simply the Cartesian product of circumsolids which are contained into orthogonal subspaces of low dimension in Rn. So in the plane, well, of course, in the plane you can take simply the product, the Cartesian product of intervals, namely rectangles. So rectangles are products of circumsolids in the plane, and in higher dimensions you have more choices. For instance, here in R3 you can see a circumsolid which is given by the Cartesian product of a regular pentagon and an interval. And so the result reads as follows. You take a convex polyhedral domain in Rn, and you assume that it is not a product of circumsolid. Then what happens is that for sufficiently small values of the parameter beta, the Rubin ground state U beta is not log concave. And as side comments, let me also specify that there is no hope to avoid this kind of non-concavity phenomenon by adding more boundary regularity on the domain omega, because it happens that if you start from a polyhedron which is not a product of circumsolid and you work with sufficiently small values of beta, it turns out that for any domain which is close to your polyhedron in Hausdorff distance, still the Rubin ground state will be not log concave. And moreover, under somewhat strengthened assumptions, one can also get a stronger conclusion, that is to say the fact that for sufficiently small beta, the level sets of U beta are, some level sets of U beta are non-convex. And how this result is obtained, why it holds for small beta, just one more slide to say a few words about their proof strategy. Well, the proof strategy is obtained as a perturbation from the Neumann case. Indeed, in the limit when beta tends to 0, the logarithm of U beta admits an asymptotic expansion of this kind, where, as you can see, there is not the term of order 0 in beta, and this is simply because up to a normalization, I can assume that the Neumann, the first Neumann eigenfunction, the first non-trivial Neumann eigenfunction is the constant equal to 1, so that its logarithm is 0, and that is why there is no term of 0 order in this expansion, and so you start directly from the first order term, which is beta v, where the function v, the derivative of of the logarithm of U beta with respect to beta, can be characterized as a unique solution to this boundary value problem. So v is constant Laplacian, and it has constant normal derivative equal to -1 along the boundary. And then there is a reminder term, a small o of beta, where this small o must be intended in a suitable topology, say in H1 or in a C1 alpha topology as well. And so in view of this expansion, it turns out that the log concavity of U beta can be put directly in relation to the concavity properties of this function v. And so what they do is a deep analysis about the concavity properties of v, and in particular, they prove a series of equivalences that I've tried to summarize here by writing just some of them. What they show is that the concavity of V is somehow equivalent to its regularity, in the sense that V is concave if and only if it is of class C2 up to the boundary. And in turn, this C2 regularity can hold if and only if V is quadratic. And this allows them to show that this concavity can be satisfied if and only if the domain omega is a product of circumsolids. And so it is clear that a strategy of this kind, which is a perturbative strategy, can give some result only in the limit when beta is small, not for all values of beta. And in particular, in the final section of their paper, they state a conjecture. They ask the following question: is it true that for a given bounded convex set in Rn, the Rubin ground state U beta becomes again log concave when beta exceeds this concavity threshold beta star? And if affirmative, is it possible to say something about how beta star depends on the space dimension and especially on the geometry of the domain omega? And so our results answered affirmatively this conjecture. So let me show you the result and try to explain it. So we start with a convex open set in Rn, which is uniformly convex and very, very smooth. So uniformly convex means simply, as usual, that the principal curvatures remain strictly positive, strictly bounded from below along the boundary. And by very smooth, I mean that it will be of class Cm with M sufficiently large. More precisely, M must satisfy this inequality where the brackets denote the integer part. So in particular, for instance, in dimension 2, our domain must be at least C5. In dimension 3, it must be at least C6, and so on. And this kind of condition, as I'm going to try to explain, comes from the fact that at some stage, you have to exploit sublevel embedding theorems. So let's say simply that we start with a uniformly convex domain, which is very, very smooth. And then under these assumptions, we can show that actually there exists a positive threshold beta star, such that when beta exceeds beta star, the Rubin ground state is strictly log concave. And moreover, we can tell something about how beta star depends not only on the space dimension, of course, and on the regularity exponent m, but specifically on the geometry of the domain omega. In fact, this beta star depends on omega through three quantities, basically. The first one is the diameter of omega, that I denote by d of omega. The second one, that I denote by delta m of omega, is the sum of the maximum of the derivatives up to order m of a function phi, which is a local parameterization of the boundary of omega in a local system of principal coordinates. So in particular, when alpha equal to the second order derivatives of the parameterization are simply the principal curvatures. And so by analogy, you may think of these higher order derivatives as higher order curvatures of the boundary. And finally, what we have here is what I denote by k-mean, which is the minimum for x varying in the boundary of the smallest principal curvature of the boundary. And let me add that the dependence of the concavity threshold beta star on these three quantities is a nice dependence in the sense that it is a continuous monotone dependence. And precisely, beta star depends in a monotone increasing way in diameter and delta m, while it depends monotonically decreasing on k-mean. So that in particular, beta star remains uniform if you look at convex domains of class Cm, for which the diameter and this maximum of higher order curvature are bounded from above, while the minimum of principal curvatures is bounded from below. If you wish, the way beta star could diverge should be if you consider domain whose diameter or whose higher order curvature tends to plus infinity, or if you consider domain for which the minimum principal curvature goes to 0. So now what I'm going to try to do is explain a little bit the proof without entering into any kind of technicality, but just trying to pass some ideas and also describe some, say, side result, which may have perhaps some autonomous interest. And so let me first say that the global approach that we use to get the result is the continuity method, which goes back to Caffarelli and Friedman in dimension 2 and in higher dimensions, but with a series of additional difficulties which come precisely from the fact that we deal with Rubin boundary conditions. So the general idea of the continuity method is the following, and let me say that this is by now a standard method in PDEs, so perhaps it is very well known to most of you, but for people who are not working in PDEs, I will try to summarize it just in this slide. So you are given your domain omega, which is the smooth and uniformly convex domain we are working with. And what one has to construct is a family of domains which give a continuous deformation from a ball to omega. And in general, in the continuity method, it is not very important how this family of deformation is constructed, but one has just to construct a continuous family of deformations. On the other hand, in our case, for the reasons I will try to explain, it is important somehow to say something about how these deformations are constructed. And in particular, the domains omega t, the family of domains omega t that we consider are of this type. They are a Minkowski convex combination of the ball and omega. Here, this plus denotes the usual Minkowski addition of sets, so that at time 0, you are at the ball, and at time 1, you arrive at our domain omega. And for every t, I denote by u beta t the Rubin-Gron state of omega t, and for shortness by v beta t, it's minus logarithm. So with this notation, our goal is to show that at time 1, that is for our domain omega, the Hessian matrix of this function v beta 1, which is minus the logarithm of u beta 1, is positive definite in the domain omega. Of course, for large values of the parameter beta. And the idea of the continuity method is to argue by contradiction. So assume that the statement in this goal is false. On the other hand, since we know that at time 0, the Hessian matrix of v beta 0 is positive definite in the ball omega 0, and this is due to the fact that, as I've already mentioned, the Rubin-Gron state of balls is strictly log concave for all values of beta, then we are in the situation when positive definiteness is true at time 0 and false at time 1. And therefore, by continuity, one can deduce that there exists some critical value of the time that I denote by S, such that for that value of the time, the Hessian matrix of beta S is still positive semi-definite, but no longer positive definite in omega S. And then one looks precisely at what happens at that critical time S. And what happens is that one can compute the Laplacian of v beta S using, of course, the quotient satisfied by u beta S. And this Laplacian turns out to be equal to the first eigenvalue plus the square of the modulus of the gradient. In particular, this right-hand side does not involve v beta S, and therefore one is in a position to apply the constant rank theorem by Korevar and Lewis, which ensures that this Hessian matrix has constant rank in the domain omega S. So what we know at this stage is that the Hessian of v beta S is not positive definite and it has constant rank. Therefore, we reach a contradiction as soon as we are able to show that the Hessian of beta S is positive definite somewhere in omega S. And this somewhere will be, of course, close to the boundary, precisely in a tubular neighborhood of the boundary of omega S. Why this? Well, because this is precisely the point where the boundary conditions come into play. And of course, we want to prove this for large values of the parameter beta. And so if you look at this new goal, this new property that we have to prove compared with the initial goal, what is the advantage? Well, the advantage is clearly what I have just said, that is to say the fact that we have to show positive definiteness not in the whole domain omega, but simply close to the boundary. And to that aim, one can exploit the boundary conditions. But on the other hand, there is somehow also a disadvantage. And the disadvantage is that while here we were working in our initial domain, the given domain omega, here we will be working in the domain omega S, where omega S is an intermediate domain for a value of S that we do not know. And in particular, since we want to prove that this property is satisfied for large values of beta, we have to pay a lot of attention on the fact that the critical value of beta must be tracked, because otherwise there is the risk that this criticality threshold might diverge when we approach our domain omega. And in that case, we don't get anything. We don't find any concavity threshold if it diverges in the limit when t tends to 1. And so we have to be very careful and keep track about the concavity threshold that we find near the boundary. And so let me show you how the strict convexity of this matrix can be proved near the boundary of the domain omega s. So when one wants to prove strict convexity near the boundary, one can start by writing the Hessian, the quadratic form associated with the Hessian of a given function u, precisely of minus the logarithm of u. And one wants to find this Hessian in terms of the derivatives of u. And this is a straightforward computation. You may write the quadratic form associated with this Hessian as the sum of two terms. The first term involves the Hessian of u, and the second term involves the gradient of u. How to prove that this quadratic form remains now positive definite in every direction near the boundary of omega? And let me first recall how things work in the Dirichlet case. While in the Dirichlet case, the argument essentially goes back to Correvar and runs as follows. One argues separately for tangential directions to the boundary and in the normal direction to the boundary. So in tangential directions, one can immediately see that among these two terms, there is only one. Why? Because the second one cancels. This is simply because under homogeneous Dirichlet boundary conditions, the gradient is orthogonal to the boundary. So in tangent direction, term 2 is 0. While term 1 is strictly positive. Why is it strictly positive? Because as you can see, there is a minus sign in front, and the Hessian matrix of any function which satisfies a Dirichlet boundary condition along the boundary is negative definite in tangential directions, because by differentiating twice the Dirichlet condition along the boundary, you get precisely that this quantity, the Hessian matrix in a tangential principal direction, is given by minus the principal curvature in that direction times the modulus of the gradient of your function which satisfies the Dirichlet condition. And so this first term gives the positive sign to this quadratic form. On the other hand, in normal direction, what happens? Well, in normal direction, none of these two addenda vanishes, but there is one which is dominant, which is the second one. Indeed, the first one is a small o of the second one, and the heuristic reason is that the first term is multiplied by 1 over u, while the second one has a factor 1 over u squared in front. And since u is going to 0, when I'm close to the boundary, the dominant term is term 2, and as you can see from its explicit expression, term 2 is positive. And this is how things go in the Dirichlet case. So what happens now in the Robin case? Well, in the Robin case, the idea is that for large beta, such case can be treated as a perturbation of the Dirichlet case. Namely, one writes the Hessian matrix of the logarithm of the Robin of minus the logarithm of the Robin ground state as the Hessian matrix of minus the logarithm of the Dirichlet ground state plus the remainder term, which is this difference. And the idea is to use the fact that we already know that in the Dirichlet case, this Hessian is positive definite. And so we can get the result if we can show that the remainder term is somehow sufficiently small. And so what one needs to prove the result is somehow a strong convergence result of Robin to Dirichlet in the limit as beta tends to plus infinity, combined with a careful control on the concavity threshold that one finds. for the reason that I have explained before. Otherwise, there is the risk that the concavity threshold might diverge and we would get anything. And so let me show you, first of all, the convergence result that we needed to set up to ensure that these Hessian matrices are close to each other with a control on the rate of convergence. So here are some global regularity and asymptotic estimates for the Robin ground state in the limit as beta tends to plus infinity, which was for us, say, the most painful part of the work. And what we could prove is the following. If you take an open set of class Cm, with no need now that it is convex, this works for arbitrary smooth open sets of class Cm, then the Robin ground state U beta is in the sublet space Hm. In particular, if M is sufficiently large, using also sublet embedding theorem, we can deduce from this kind of regularity result that U beta converges to UD, the Dirichlet ground state, in a quite strong topology, that is to say in the C2 topology, with a rate of convergence which is controlled. Precisely the C2 norm of this difference is less than or equal to a positive constant m divided by beta, where it is important for us to know that this positive constant m depends on the geometry of omega. Precisely depends on the diameter, on the boundary curvatures up to order m, and on the first Dirichlet eigenvalues. And these up arrows here are to denote that the dependence of m on these three quantities is a monotone increasing continuous dependence, which is important for our purposes. And along the way, we can also get a convergence result for the full spectrum, which states that the Robin eigenvalues converge to Dirichlet one in the limit as beta tends to plus infinity, again with a rate of convergence of order 1 over beta, with a constant capital lambda k, which now depends still in a monotone increasing way from delta 2, and from the Dirichlet eigenvalue of order k. I have to mention that this kind of results were already proved in a series of papers in 2014 by Filinowski, but without keeping track of the constants, without keeping track of the dependence of the constants on the geometry of the domain, which for us is a crucial point. And this is precisely the reason why we needed to give a new proof which takes into account the dependence on the geometry. And let me also say that as a byproduct of this convergence result for the spectrum, we can obtain a lower bound for the Robin gap of convex C2 domains, which is of the same kind predicted by Anders, Clutterbuck, and Auer, even if they also work more in general with Schrödinger operators with convex potentials, while we consider only the case when the potential is 0. Anyhow, what we obtain is that this difference is bounded from below by 3 pi squared divided by the diameter minus 1 over beta times the constant. And unfortunately, this constant, in view of the method that we use for the proof, involves the curvature of the boundary curvature, the maximum boundary curvature K max. So in particular, this is not a universal constant, and it will diverge if you consider domains which may tend to have some singularity. And now going back to our goal, going back to the goal of showing the strict convexity near the boundary, if we apply these asymptotic estimates as beta tends to plus infinity, what we are able to show is that actually the Hessian matrix of minus the logarithm of U beta is a positive definite matrix for all x in a neighborhood of the boundary, for all direction eta of the unit sphere, and for beta larger than a critical threshold beta star. And we can prove this inequality similarly as in the Dirichlet case by arguing separately for tangential, say almost tangential directions, and for directions which are close to the normal direction to the boundary. And what I have to comment on is the criticality threshold the critical concavity threshold beta star, since beta star turns out to depend on several quantities. As you can see here, beta star depends on 5 quantities. The first 3 quantities are in red because they are purely geometric quantities. As before, up arrows denote a monotone increasing dependence, while down arrow denote a monotone decreasing dependence. So these 3 quantities are purely geometrical and are the 3 quantities that you have seen in the statement: the diameter, the boundary curvatures up to order m, and the minimum principal curvature. While the 4th and 5th quantities are in blue because they're not purely geometrical, and they are precisely the first Dirichlet eigenvalue of omega, and what I denote here by Q of omega, which is the minimum along the boundary of the modulus of the gradient of the Dirichlet ground state. And so from these 3 quantities, you may argue that some of them, specifically the diameter, delta m and lambda 1, come precisely from the previous result of convergence of Robin to Dirichlet, while the other one, specifically k-mean and the Dirichlet eigenvalue, comes from the kind of estimate that we make here when working with this Hessian matrix, in particular with this first order term. And so the crucial question that we have to answer to conclude the proof is the following: is this concavity threshold beta star uniform when omega varies in the family of sets omega t for t in 0, 1? And this is precisely the point where it is important to know that the continuous family of perturbation is of this type. And in fact, the answer to this question is yes, the threshold beta star is uniform when t varies from 0 to 1, because first of all, these sets omega t are themselves all of class Cm. They enjoy the same regularity as our initial domain, and this comes from some properties of the Minkowski addition of convex smooth sets due to Gomi. And we are able to prove that when t varies in 0, 1, the red quantities, the geometric quantities, remain bounded. Precisely the ones with up arrow remain bounded from above, while k-mean, which has a down arrow, remains bounded from below. And especially that the blue quantities remain controlled by the red one. Why this? Well, for the Dirichlet eigenvalue, it is simple. We have to prove that lambda 1d remains bounded from above, because here we have a monotone increasing dependence. And to bound lambda 1d from above, one can use the fact that lambda 1 is monotone decreasing under set inclusion. And in view of the bounds, that geometric bounds that we have on our domains, they contain a uniform sphere condition, they contain a uniform interior sphere condition, and so we can estimate lambda 1 from above by the eigenvalue of this interior sphere. And what is less immediate to show is that the minimum of the gradient of UD remains uniformly bounded in terms of these 3 quantities when t varies from 0 to 1. To that purpose, we had to settle a boundary gradient estimate for the Dirichlet ground state of a convex domain which satisfies a uniform interior sphere condition. Actually, we were not able to find such a result in the literature, so we had to settle it. And here is the statement. I don't want to enter into the details now, but what you can see here in the right-hand side, in this lower bound for the gradient of the Dirichlet ground state, are some, say, dimensional constants. And besides this dimensional constant, we have some geometric quantities with a very good dependence. And these geometric quantities are essentially the diameter, the in radius, and again, the radius of interior sphere. So all these are quantities that remain controlled in our deformation process when t varies from 0 to 1. And let me add that for this result, we are indebted to David Gerson, who kindly suggested us how to proceed. In particular, what we had to use was an estimate for the location of the hotspot, namely the point where UD reaches its maximum, which by Biswas and Lurinsky cannot be too close to the boundary. And once you know that this hotspot is not too close to the boundary, you can construct a Harnack chain of bolts inspired to the papers by Gerson about the behavior of the Dirichlet-Grund state on convex domains and get your lower bound for the modulus of the gradient of UD. So this way, we could obtain that also Q remains uniformly bounded when T varies in 0, 1, so that the threshold remains uniform, and we are able to conclude the proof. So if I still have 2 minutes more, I would like to add just a few words to say that we have the same result, an analogous result, also for the Robin torsion function. Here I've written the result. As you can see, it reads exactly the same. Under the same kind of assumption, we have again a concavity threshold that now I denote beta star star, and this concavity threshold for the Robin torsion function turns out to depend exactly on the same 3 geometric quantities. And finally, among the many open questions, let me comment briefly some of them. Well, in general, I would say that it would be very, very desirable to get a better understanding of this interplay between concavity properties of solution and geometry of the domain. For instance, of course, we would be very glad if it would be possible to remove or at least weaken the assumptions of our result. But at the moment, we are not able to prove it without these very strong regularity assumptions. We do not know if they are really necessary. In particular, we do not know what happens even for very simple geometries, even in the plane, such as triangles or circular sectors. Is it true that the Robin-Grund state is log concave for all values of beta or not? More in general, apart from balls and rectangles, is it true that there are some other domains for which the Robin-Grund state is log concave for all values of beta? And if affirmative, is it possible to characterize such kind of domains? So as you have seen, somehow what the proof of the result by Anders Clutterbuck and Hauer and our results have in common is the fact that they are obtained through a perturbative argument. And in this respect, it is clear that through a perturbative argument, one can only get some result either for beta small, where the result is found as a perturbation of the Neumann case, or for beta large, where the result is found as a perturbation of the Dirichlet case. But if one wants to get a result only for all values of beta, maybe it is needed to invent somehow some new method different from the ones which are used in the Dirichlet case, which do not work at all when dealing with Robin boundary conditions. And finally, another slightly different but still related question, still about concavity properties, which I would be very much interested to learn something about, is what happens for Broom-Minkowski type inequalities for Robin energies. In fact, Braskamp and Lieb could also prove that the Dirichlet-Grund state of convex domains omega satisfies a Broom-Minkowski type inequality, which is fully analogous to the one satisfied by volume. And so it is a very natural question to wonder whether also for the Robin-Grund state or for the Robin torsional rigidity, this is still the case. And as far as I know, in this direction, there is no result known, not even a partial one, not even for beta large or whatever else. And so I would be very interested in learning something about this question. So I think I have to stop now. Thanks a lot for your time, for your attention.
Thanks very much, Ilaria. Wonderful talk. If anybody would like to ask a question, I believe you can raise your hand and we can give you permission to unmute. So please feel free to do that. I had a couple of questions just to start with. So the dependence on the dimension at the moment comes only through the use of the Sobolev inequality. Is that right? So the main thing
Yeah.
you need to prove is good C2 estimates. But to get that, you go through some high Sobolev estimate and then Sobolev. Yeah. So yeah, I mean, is it possible then to prove more directly a C2 alpha estimate up to the boundary, for example, without going through the Sobolev theory?
I don't know. I don't know. This is
Sure.
We are not experts at all about regularity theory, and so let me show them. And so this was the way we found to proceed, but I'm not sure that it is the only way. Huh?
Yeah. No, it seems
we're not all experts. Maybe there are in the audience, I don't know, some experts about regularity, which who will find naive this the way to proceed. I don't know.
It would be interesting to know, yeah, because I guess in that case your result would improve to one depending only on, let's say, diameter and then upper and lower bounds on principal curvatures, for example, which would be would be quite nice.
Course, it would be great to obtain this. I do not know.
Yeah.
For us, already the Sobolev regularity was relatively new in the sense that it was contained in some monograph, in the monograph by Mikhailov. The monograph, classical monograph in PDE, the Sobolev regularity is already contained, and so we tried somehow to follow his arguments because.
Right, that's very interesting. Yeah. So also that you mentioned the possibility of including, say, a convex potential, which of course is interesting works out very nicely in the Dirichlet case, but that seems to be an obstacle in all the other cases, even the Neumann case. Right? I guess there's immediately you don't know anything about the.
Yes, I have to say that we have not explored that direction. We have always worked with the zero potential.
Sure, that's already hard enough.
but it would be definitely interesting to include it if possible.
Yeah. Very good. Okay, I don't see any raised hands so far. I think everybody should have received an invitation to the coffee break. It should be a separate email that arrived sometime during the talk. So please feel free to come along. Everyone's welcome. Just to have a chat, talk about either the talk or whatever else you would like to talk about. And that will maybe start after 5 minutes or so. It gives everyone a chance to get an actual cup of coffee. If there are no other questions, then thank you, Ilaria, and thanks everyone for attending. And we'll see you in a few minutes in the coffee break.
Okay, thank you. Bye.
Bye.
So we can close the meeting now.
Yeah, okay. So we'll see you, follow the other link and see you soon.
See you, thanks.
Thanks, Ilaria.
Thanks.
See you.